Beyond the orbits of Neptune and Pluto lies a frozen graveyard of cosmic secrets, a place where sunlight is nothing more than a faint glimmer, and objects older than Earth itself drift in the endless dark. This is the Kuiper Belt, a sprawling frontier at the edge of our solar system, packed with mysteries that challenge everything we think we know about how planets form. Hidden among its icy shadows are worlds shaped like snowmen, dwarf planets with underground oceans, and fragments of the solar system's violent infancy, each one a puzzle waiting to be solved. Some of these objects follow orbits so strange they hint at unseen planets lurking even farther out, while others might hold clues to how life's building blocks first arrived on Earth. Today, we're pulling back the curtain on 25 of the most bizarre and enigmatic objects ever discovered in this frozen wilderness. From Pluto's beating heart to a distant wanderer with an 11,000-year orbit, each of these cosmic oddballs tells a story that rewrites the rules of our celestial neighborhood. Strap in, because what lies ahead will make you question how well we truly know our own solar system. The deeper we go, the stranger it gets, and the best part: we've barely scratched the surface. Now let's turn our attention to the first stop on this journey through the Kuiper Belt's greatest hits, a world so strange, it looks like it was sculpted by a cosmic artist with a sense of humor. Meet Arrokoth, formerly known as Ultima Thule, the most distant object ever visited by a spacecraft. When NASA New Horizons probe raced past it on New Year's Day 2019, scientists got their first close-up look at a pristine relic from the dawn of the solar system. And what they saw was nothing short of astonishing. This tiny world, no bigger than a city, is shaped like a lopsided snowman, two distinct lobes gently pressed together in what scientists call a contact binary. The larger lobe, nicknamed Ultima, smooshes against the smaller one, Thule, in a cosmic embrace that's lasted over 4 billion years. This bizarre structure suggests Arrokoth wasn't born from violent collisions, but from two separate objects that drifted together so slowly they stuck like celestial Velcro. Imagine two snowballs gently touching in zero gravity and just staying that way. That's the peaceful origin story Arrokoth whispers to us from the frigid depths of space. But its shape isn't the only oddity. Arrokoth wears a coat of deep reddish hues, likely from organic molecules called tholins, the same stuff that gives Pluto its rusty tint. These compounds form when methane and nitrogen ice get zapped by cosmic rays over billions of years, essentially turning into cosmic barbecue sauce. And here's the kicker: that red surface is smooth, almost untouched by the scars of impact. That's like finding a 4-billion-year-old fossil without a single crack. It tells us Arrokoth has been chilling in the Kuiper Belt's deep freeze since the solar system's infancy, avoiding the chaos that reshaped planets closer to the Sun. Even its spin is weirdly relaxed. Arrokoth takes a leisurely 15 hours to complete a single rotation, slower than most Kuiper Belt objects. This sluggish twirl hints that it never experienced the gravitational kicks or collisions that would have sped it up. Put simply, it's the solar system's version of a sleeping baby, undisturbed, pristine, and full of secrets about how planets like Earth first came together. So what does this snowman-shaped time capsule teach us? That the early solar system wasn't just a demolition derby of crashing rocks. Some worlds formed gently, in slow-motion dances at the edge of the light. Arrokoth is a fossilized snapshot of that quieter era, proving that sometimes the universe prefers a whisper to a bang. And if this is just our first up-close look at a Kuiper Belt object, imagine what else is waiting out there, frozen in time. Up next, we'll zoom in even closer to explore Arrokoth's eerily smooth surface, and why its lack of craters has scientists scratching their heads. Now let's take a closer look at Arrokoth's surface, because this is where things get even stranger. If you were expecting a battered, cratered landscape like many other ancient worlds in our solar system, prepare to be surprised. Arrokoth's face is eerily smooth, with vast stretches that appear almost untouched by the violent collisions that shaped most of our cosmic neighborhood. It's as if this tiny world was preserved in a celestial time capsule, frozen in its original state for billions of years. Scientists were stunned when New Horizons beamed back images showing only a handful of faint depressions that might be craters. The lack of obvious impact scars suggests Arrokoth has spent its entire existence in one of the quietest corners of the solar system, avoiding the chaotic traffic of flying debris. But how does an object survive 4 billion years without getting pummeled? The answer might lie in its remote location, tucked away in the Kuiper Belt's sparsely populated outskirts. With fewer objects buzzing around, the chances of a direct hit drop dramatically. But there's another puzzle. Even if collisions were rare, shouldn't there be some craters? That's where the concept of streaming instability comes into play. This theory suggests that Arrokoth didn't form from a series of violent crashes, but rather from a gentle dance of tiny particles in the early solar system's protoplanetary disk. Imagine a cosmic snow globe where dust and ice grains gradually clump together, sticking softly due to static electricity or other weak forces. Over time, these clumps grow larger, eventually forming objects like Arrokoth's two lobes, which then gently merge. If this process was slow and delicate enough, it could explain the absence of large impact scars because there simply weren't many high-speed collisions involved in its birth. The smoothness of Arrokoth's surface might also hint at another fascinating possibility: self-healing terrain. Some researchers propose that over eons, volatile ices like methane or nitrogen could have sublimated, turning directly from solid to gas, and then refrosted elsewhere, effectively resurfacing the object. Think of it as a slow-motion facelift, where the surface subtly refreshes itself over billions of years, erasing small craters or cracks in the process. Yet perhaps the most striking feature is a series of faint, aligned pits and ridges along the neck where the two lobes connect. These could be remnants of the merging process wrinkles formed when Ultima and Thule snuggled together. Alternatively, they might be signs of ancient fractures from internal stresses as the object cooled and settled. Either way, these subtle textures are like reading the faint handwriting of the solar system's early days preserved in ice. So what does all this mean for our understanding of planet formation? Arrokoth challenges the old idea that all building blocks of planets had to endure violent crashes. Instead, it paints a picture of a gentler nursery where some worlds assembled themselves like cosmic snowflakes, slowly, quietly, and with remarkable care. And if this is how Arrokoth came to be, how many other pristine relics are still drifting out there, waiting to tell their stories? As we continue our journey, we'll shift focus to another iconic resident of the Kuiper Belt, Pluto, the dwarf planet that refuses to be forgotten, with its towering ice mountains and shimmering atmosphere. Now let's turn our attention to Pluto, a world that refuses to be defined by labels. While its reclassification as a dwarf planet might have made headlines, what truly matters is the astonishing activity happening on its surface. Forget the frozen, lifeless rock many imagine. Pluto is a geologically vibrant world with landscapes that rival Earth's in complexity. Picture this: nitrogen glaciers creeping across vast plains, dwarfing even the ice sheets of Antarctica. One of the most striking features is Sputnik Planitia, a heart-shaped basin filled with frozen nitrogen that behaves almost like a slow-moving river. Scientists believe this glacier might still be flowing today, reshaping Pluto's surface over time. Then there's the towering water ice mountains, some reaching heights comparable to the Rockies, their peaks coated in exotic ices like methane snow. And above it all, a hazy blue atmosphere stretches high into the sky, created by sunlight breaking apart methane molecules and forming complex organic compounds. But let's address the elephant in the room: Pluto's demotion. The truth is, this wasn't a downgrade but a clarification. The term dwarf planet doesn't mean Pluto is unimportant. In fact, it's a testament to how unique it is. Unlike the 8 classical planets, Pluto shares its orbital neighborhood with other Kuiper Belt objects, but that doesn't make it any less fascinating. If anything, its reclassification sparked a revolution in our understanding of the solar system's diversity. What truly sets Pluto apart is its geological heartbeat. NASA's New Horizons mission revealed cracks, ridges, and even possible cryovolcanoes, hints that internal heat might still be at work. Some researchers speculate a subsurface ocean could exist beneath its icy shell, kept liquid by radioactive decay or tidal interactions with its largest moon, Charon. Pluto's atmosphere holds surprises too. It's not static but breathes with the seasons. As Pluto moves along its elongated orbit, atmospheric gases freeze onto the surface or sublimate back into the sky, creating a dynamic cycle. So forget the outdated idea of Pluto as a lonely, frozen outcast. It's a dynamic world with processes that mirror Earth's, just in extreme slow motion. And as we'll see next, its secrets might be even deeper than we thought. Now, let's dive beneath the surface, literally. While Pluto's icy exterior is mesmerizing, some of its most profound mysteries might be hiding deep below, in what scientists suspect could be a vast subsurface ocean. The clues to this hidden world lie in Pluto's iconic heart, Sputnik Planitia. This massive basin, roughly the size of Texas, isn't just a geological oddity, it's a gravitational anomaly. Data from New Horizons revealed that Pluto's heart exerts an unusually strong pull on the dwarf planet, suggesting something dense or massive beneath it. One leading theory, a subsurface ocean, possibly kept liquid by the heat of radioactive elements like potassium and uranium decaying in Pluto's rocky core. But here's the twist: unlike Earth's oceans, this one wouldn't be sloshing freely. Instead, it's likely sandwiched between layers of ice, a thick, slushy layer insulated by the overlying shell. Then there's the role of Charon, Pluto's largest moon. The two are tidally locked, forever facing each other in a cosmic dance. This gravitational tug of war could generate friction inside Pluto, flexing its interior like a rubber ball and producing enough heat to keep water from freezing entirely. Imagine the slow, rhythmic squeezing of a stress toy, except on a planetary scale, over billions of years. But how do we know this ocean exists if we can't see it? The evidence is written in Pluto's cracks. The surface around Sputnik Planitia is scarred with fractures, similar to the stretch marks on a balloon as it inflates. These suggest the basin has been expanding, possibly because water beneath it froze long ago and expanded, or because the ocean below is still slowly freezing today, pushing the ice above outward. Even more telling are the strange, polygon-shaped patterns in Sputnik's nitrogen ice features that on Earth often form over bodies of water, like the cracks in a frozen lake. The presence of an ocean would also explain Pluto's surprising lack of a wobble. Normally, a spinning object like Pluto would teeter slightly if its mass weren't evenly distributed. But Sputnik Planitia sits almost perfectly opposite Charon, as if something like a dense underground sea shifted Pluto's weight to balance it out. Some scientists think this means the entire basin might have slid over time, dragged by the ocean beneath like a cargo ship shifting its ballast. Now picture the implications. If Pluto has liquid water, even in this bizarre, slushy form, it joins a growing list of icy worlds like Europa and Enceladus, where the ingredients for life might exist. The heat, the water, and the organic molecules in Pluto's atmosphere could create a niche where chemistry becomes biology. It's a long shot, but it's a reminder. The solar system's most habitable spots might not be where we expect. So while Pluto's surface is a frozen masterpiece, its true masterpiece might lie hidden, a secret ocean, whispering to us through cracks and gravity. And as we move forward, keep this in mind. If even a distant, sunless world like Pluto can defy expectations, what else might be waiting in the Kuiper Belt shadows? Now let's journey beyond Pluto to a world that single-handedly reshaped our understanding of what makes a planet Eris. Discovered in 2005, this icy dwarf planet sent shockwaves through the scientific community, not just for its size but for the existential crisis it sparked. Eris is slightly more massive than Pluto, with a diameter just a hair smaller, yet its sheer density suggests a rockier core, making it a heavyweight in the Kuiper Belt. What makes Eris truly stand out is its blindingly bright surface, one of the most reflective in the solar system. Imagine a cosmic mirror coated in nitrogen frost, bouncing back nearly all the sunlight that touches it. This high albedo hints at a surface constantly refreshed by geologic activity, possibly cryovolcanism, or seasonal shifts where volatile gases like methane and nitrogen freeze and sublimate under the weak sunlight. Unlike Pluto's complex terrain, Eris's surface appears eerily uniform, as if draped in a smooth, frosty blanket. But beneath that frost, astronomers suspect a dynamic world, with temperatures hovering around -400 degrees Fahrenheit, cold enough to turn air into snow. Then there's Eris's orbit, a cosmic rebellion against the solar system's orderly plane. While most planets and dwarf planets orbit near the ecliptic, Eris tilts a staggering 44 degrees, tracing a path that takes it from 38 astronomical units to nearly 100 astronomical units from the Sun. This extreme elliptical orbit suggests a turbulent past, perhaps a gravitational kick from Neptune or a close encounter with another massive object. Some theories even propose that Eris was once part of the inner Kuiper Belt before being flung into its current lonely, tilted path. But Eris's legacy isn't just about its physical traits. Its discovery forced astronomers to confront a pivotal question: what is a planet? Pluto's demotion in 2006 wasn't just about size. It was about Eris proving that the solar system might be teeming with Pluto-like worlds. Suddenly, the word planet needed boundaries. The International Astronomical Union's new definition, requiring a body to clear its orbit, left Pluto and Eris as dwarf planets, a decision still debated today. Eris, in essence, became the celestial wrench that broke the planetary mold. Yet for all its controversy, Eris remains enigmatic. No spacecraft has visited it, leaving its secrets locked in ice. Does it harbor cryovolcanoes like Pluto? Could its density hint at a subsurface ocean? Or is it simply a rocky core wrapped in ice? And what of its seasonal cycles, lasting centuries in the dim light of the distant sun? Every unanswered question reminds us that the Kuiper Belt isn't just a graveyard of relics, it's a dynamic frontier, where worlds like Eris rewrite the rules as we uncover them. So while Pluto may be the Kuiper Belt's celebrity, Eris is its revolutionary, a frozen provocateur that challenged our cosmic taxonomy and won. And as we'll soon see, its moon Dysnomia adds yet another twist to this icy saga. Now, let's turn our attention to the silent companion orbiting this cosmic rebel Dysnomia. Named after the Greek spirit of lawlessness, fittingly paired with Eris, the goddess of discord, this moon might seem like a mere footnote, but its dance around Eris reveals secrets about the dwarf planet's hidden depths. Dysnomia is small, only about 150 miles in diameter, but its orbit is a treasure trove of clues, circling Eris every 16 days in a nearly circular path. Dysnomia's movements allow astronomers to calculate Eris's mass with precision, confirming it's denser than Pluto, likely packed with more rock beneath its icy shell. The way Dysnomia orbits Eris also hints at a violent past. Most moons in the Kuiper Belt, like Pluto's Charon, are thought to have formed from colossal collisions, a chaotic era when objects slammed into each other, scattering debris that later coalesced into moons. Dysnomia's tidy, close orbit suggests it might be a surviving fragment of such a cataclysmic crash, a relic from a time when the Kuiper Belt was a demolition derby of icy bodies. But here's the twist: Dysnomia's orbit is almost too perfect. If Eris had been jostled by gravitational encounters, say with Neptune, Dysnomia's path should show more irregularities. Its stability implies Eris has been cruising in its tilted, distant orbit for billions of years, undisturbed. That raises a tantalizing question. Did Eris form already on the fringes of the solar system, or was it flung there so early that Dysnomia's orbit had time to settle into this serene rhythm? Then there's the enigma of Eris's interior. Dysnomia's gravitational tug suggests Eris isn't just a uniform ball of ice and rock. Variations in density could mean a layered structure, perhaps a rocky core, a mantle of slushy water, and a crust of nitrogen and methane ice. And if Eris's interior is still warm from radioactive decay, could it, like Pluto, harbor cryovolcanoes? The smooth, reflective surface might hide cracks where volatile gases erupt, refreezing into that glossy frost. Without a spacecraft's close-up view, we're left with echoes. The way Dysnomia wobbles, the way light scatters off Eris's surface, all whispering possibilities. Dysnomia's dark surface adds another puzzle. While Eris shines brilliantly, its moon is a dim spectre reflecting less than 5% of sunlight. This stark contrast suggests Dysnomia's composition is fundamentally different, maybe rich in carbon compounds, the primordial leftovers of solar system formation. If so, it's a time capsule preserving chemistry from an era before planets took shape. The duo of Eris and Dysnomia embodies the Kuiper Belt's contradictions. A dazzling dwarf planet with a shadowy moon, a rebellious orbit paired with an orderly companion, a world that forced us to redefine planets yet remains defiantly mysterious. As we venture further into the belt, remember, each of these icy realms isn't just a frozen rock. They're storytellers, and Dysnomia's silent orbit is just one more chapter in their epic. Now, let's shift our focus to another intriguing denizen of the Kuiper Belt, Makemake, a world that stands out for its striking reddish hue and its puzzling lack of an atmosphere. Named after the creation deity of the Rapa Nui people of Easter Island, Makemake is a dwarf planet that challenges our understanding of how these distant icy bodies behave. While Pluto boasts a complex, hazy atmosphere and seasonal changes, Makemake presents a stark contrast, a seemingly barren, methane-coated surface with no detectable atmosphere to speak of. So, what makes Makemake so different? The answer lies in its size, temperature, and composition. Makemake is smaller than Pluto, with a diameter of roughly 880 miles, which means its gravity isn't strong enough to hold onto volatile gases like nitrogen or methane for long periods. But here's the twist. Makemake's surface is covered in methane, frozen solid in the frigid temperatures of the Kuiper Belt. This creates a paradox. Methane is present, yet no atmosphere is detected. The key is in the temperature. Unlike Pluto, which experiences enough warmth from the sun even at its vast distance to sublimate some of its ices into a thin atmosphere, Makemake's orbit keeps it just a bit colder. Without that critical temperature threshold, the methane stays locked in ice, never vaporizing enough to form a sustained gaseous envelope. Another factor is Makemake's reflectivity, or albedo. Its surface is highly reflective, bouncing back much of the sun's feeble light. This means it absorbs less heat, further keeping temperatures too low for ices to sublimate. Compare this to Pluto, where darker patches of Tholen's complex organic molecules absorb more sunlight, creating localized warming that helps sustain its atmosphere. Makemake, in contrast, is like a cosmic mirror, staying cold and quiet, but the story doesn't end there. Observations suggest Makemake might have transient atmospheres, thin, seasonal hazes that appear briefly when it reaches the closest point in its orbit to the sun. During these fleeting moments, pockets of methane or nitrogen might vaporize, creating a temporary shroud before freezing back onto the surface. This would make Makemake a world in flux, cycling between dormancy and brief atmospheric activity. The absence of an atmosphere also affects Makemake's surface. Without wind or weather to erode it, the terrain remains eerily pristine, likely scarred only by the occasional impact. Scientists suspect its reddish color comes from the effects of cosmic radiation bombarding the methane ice over billions of years, breaking it down into complex hydrocarbons that give it that distinctive rusty tint. What's fascinating is how Makemake's differences with Pluto underline the diversity of the Kuiper Belt. Some worlds, like Pluto, are dynamic and ever-changing, while others, like Makemake, are frozen time capsules, preserving ancient surfaces untouched by atmospheric erosion. This variation tells us that distance, size, and composition all play crucial roles in shaping these distant worlds, and that the Kuiper Belt is far from a monotonous expanse of ice. As we continue our journey through this remote region, keep in mind that each object, whether shrouded in haze or bare to the void, has its own story to tell. And Makemake's tale is one of quiet resilience, a world that refuses to conform to our expectations. Just when we thought we had Makemake figured out, this enigmatic world surprised us once more. In 2016, astronomers peering through the Hubble Space Telescope spotted something unexpected, a faint, dark companion trailing Makemake in its orbit. This shadowy moon, officially designated MK2 but nicknamed Makemake's moon, was a revelation. Here's why its discovery turned our understanding of the Kuiper Belt upside down. MK2 is no ordinary moon. For starters, it's incredibly dark, reflecting only about 4% of the sunlight that hits it, darker than charcoal. That's a stark contrast to Makemake's brilliant, reflective surface. Scientists believe MK2 darkness comes from a coating of complex organic compounds, similar to the material found on comets, baked by eons of cosmic radiation. But the real puzzle is how such a dark moon ended up orbiting such a bright world. One theory suggests MK2 might be a captured object, a wandering Kuiper Belt body snared by Makemake's gravity long ago. Another possibility, it could be a fragment from a colossal impact, much like how Earth's moon formed, except MK2's eerie darkness hints at a very different origin story. The moon's orbit adds another layer of mystery. MK2 circles Makemake at a distance of about 13,000 miles, but its path is tilted at an angle, suggesting it wasn't born from a neat equatorial collision. This irregular orbit challenges the prevailing idea that most Kuiper Belt moons form from gentle mergers or impacts in the early solar system. Instead, MK2's trajectory implies a chaotic past, perhaps a violent encounter that hurled debris into a lopsided orbit. Even more intriguing, MK2's presence might explain why Makemake lacks the bright, reflective frost seen on other dwarf planets. Some researchers propose that MK2's gravity could be shepherding smaller particles away from Makemake, preventing them from settling on its surface and brightening it further. Then there's the question of size. MK2 is tiny, only about 100 miles across, making it one of the smallest known moons in the Kuiper Belt. Its diminutive stature raises eyebrows because, according to current models, moons this small shouldn't be common around dwarf planets. Most Kuiper Belt moons are thought to form from massive collisions, which typically produce larger satellites. MK2's existence suggests that either our models are incomplete or that the Kuiper Belt's moon-making processes are far more diverse than we imagined. Perhaps the most tantalizing clue lies in what we haven't found. Despite intensive searches, no other moons have been detected around Makemake. This makes MK2 an only child, adding to the peculiarity. In contrast, dwarf planets like Pluto and Haumea host multiple moons, each with their own quirks. MK2's solitude hints that Makemake's system might be the product of a unique, one-off event, a cosmic accident that left behind this single, shadowy witness. The discovery of MK2 didn't just give us a new moon to study, it forced us to rethink how satellites form in the frigid outskirts of our solar system. Every time we assume we've cracked the Kuiper Belt's code, objects like MK2 remind us that the rules are still being written. As we turn our gaze to the next mysterious world in this distant realm, keep in mind that even the darkest, smallest companions can hold the brightest clues to our solar system's untold stories. Now, let's shift our focus to one of the most bizarre and fast-moving objects in the Kuiper Belt, Haumea. Picture a cosmic football tumbling through space at breakneck speed, and you've got this dwarf planet in a nutshell. Haumea isn't just another icy rock. It's a world spinning so fast it's been stretched into an elongated shape, completing a full rotation in just under 4 hours. That's faster than any other large body in our solar system, and it raises a glaring question: how did it end up with such dizzying momentum? Scientists believe Haumea's wild spin is the aftermath of a colossal collision billions of years ago. This impact didn't just reshape the dwarf planet, it also gave birth to what we now call Haumea's collisional family, a group of smaller, icy fragments sharing similar orbits and compositions. These fragments are like cosmic breadcrumbs, hinting at the violent event that scattered them across the Kuiper Belt. But here's the twist: Haumea's family isn't just a random assortment of debris. Their nearly identical surface compositions, rich in water ice, suggest they were all once part of the same parent body. This makes Haumea's family one of the few known examples of a planetary-scale breakup in our solar system's distant past. Then there's Haumea's dazzling brightness. Its albedo, or reflectivity, is exceptionally high, rivaling that of fresh snow. This is puzzling because most Kuiper Belt objects darken over time due to radiation and cosmic rays. So why does Haumea gleam so brightly? One leading theory points to cryovolcanism, eruptions of water ice that resurface the dwarf planet, keeping it pristine. Another idea suggests that Haumea's rapid rotation flings loose, bright ice particles into space, which then settle back onto its surface like a constant frosty snowfall. Either way, its brilliance defies expectations, making it a standout even among its icy neighbors. But Haumea's surprises don't end there. In 2017, astronomers discovered something no one expected: a ring. That's right, Haumea joins the ranks of Saturn and Uranus as one of the few solar system bodies known to have a ring system. This thin, dark band orbits Haumea at a distance of about 1,000 miles, likely made up of shattered ice and rock from yet another ancient collision. Rings are rare in the Kuiper Belt, and Haumea's challenges our assumptions about how and where they can form. And let's not forget Haumea's two moons, Haumea and Namaka. These tiny companions have chaotic, elliptical orbits, adding another layer of intrigue. Some researchers think their erratic paths are the result of gravitational tugs from Haumea's irregular shape, while others speculate they might be captured members of its collisional family. Either way, their dance around Haumea is a far cry from the orderly orbits of most planetary moons. From its breakneck spin to its glittering surface and mysterious ring, Haumea is a testament to the Kuiper Belt's capacity for surprise. It's a world where the laws of physics seem to bend, where collisions don't just destroy, they create. And as we'll soon see, the Kuiper Belt has even more peculiar worlds waiting to challenge our understanding. Let's take a closer look at Haumea's rings and moons, because this dwarf planet's entourage is just as fascinating as the world itself. When astronomers first spotted a faint, narrow ring circling Haumea in 2017, it sent shockwaves through the scientific community. Rings are already rare in our solar system, and finding one around a Kuiper Belt object was like discovering a hidden gem in the most unexpected place. This ring isn't just a thin, decorative loop. It's a cosmic crime scene, likely formed from the debris of a violent collision. Imagine two icy bodies smashing into each other with such force that the wreckage didn't just scatter, it organized itself into a neat, circular band around Haumea. What's even more intriguing is how this ring manages to stay intact despite Haumea's chaotic spin. Normally, you'd expect such rapid rotation to fling debris away, but here, gravity and motion have struck a delicate balance, creating a stable orbit for this icy halo. Now let's talk about Haumea's moons, Haumea and Namaka. These two aren't your typical, well-behaved satellites. Haumea, the larger of the pair, orbits at a leisurely pace, taking roughly 49 days to circle Haumea. But Namaka, its path is a wild, unpredictable dance, sometimes swinging close to Haumea, other times veering far away. This irregularity hints at a turbulent past. Some scientists think these moons might be remnants of the same colossal impact that gave Haumea its dizzying spin and collisional family. Others propose that Namaka's erratic orbit could be the result of gravitational tugs from Haumea, turning their shared space into a cosmic tug-of-war. Either way, their movements are a far cry from the orderly, clockwork orbits we see around planets like Earth or Jupiter. Here's where it gets even more interesting. Haumea's rapid rotation and elongated shape create a gravitational environment unlike anything else in the Kuiper Belt. Most moons orbit along their parent body's equator, but Haumea's odd shape means its gravity is lumpy and uneven. This could explain why Namaka's orbit is so chaotic. It's constantly being nudged and pulled by Haumea's irregular gravitational field. Think of it like trying to walk straight on a ship tossed by waves. The path is never smooth. What does all this tell us? Haumea's rings and moons are more than just curiosities. They're clues to the Kuiper Belt's violent history. Collisions weren't just occasional events here. They were transformative, reshaping worlds and birthing new ones. The fact that Haumea's ring exists at all challenges our assumptions about where and how rings can form, proving that even in the frigid outskirts of the solar system, dynamic processes are at work. And its moons, they're living proof that chaos and order can coexist, offering a glimpse into the gravitational puzzles that still baffle astronomers. As we move forward, keep Haumea's wild family in mind because the Kuiper Belt is full of worlds that refuse to play by the rules. Up next, we'll explore another object that defies expectations, proving once again that the outer solar system is anything but predictable. Now, let's turn our attention to Kuiper, a world that's rewriting the rules of ring systems. Nestled in the Kuiper Belt, Kuiper isn't just another icy rock. It's a cosmic rebel with a ring that shouldn't exist. Most rings, like Saturn's iconic loops, form inside what's called the Roche limit, the zone where a planet's gravity tears apart any large object that ventures too close. But Kuiper's ring laughs in the face of this rule. It orbits far beyond this limit, in a region where particles should have coalesced into a moon billions of years ago. So why hasn't it? That's the mystery gripping astronomers. One leading theory suggests that Kuiper's ring might be held together by invisible shepherds, tiny, unseen moons whose gravity corrals the debris, preventing it from clumping together. Alternatively, the ring's particles could be exceptionally bouncy, colliding just enough to stay loose but not enough to stick. Imagine a cosmic dance where every step is perfectly timed to avoid tripping. But here's the twist. Kuiper's ring isn't just defying expectations. It's forcing us to reconsider how rings form across the universe. If rings can exist beyond the Roche limit, could other distant worlds harbor similar surprises? Kuiper's defiance doesn't stop there. This icy world might also host volcanoes that spew slushy mixtures of water, ammonia, or methane instead of molten rock. While we haven't caught one in the act, Kuiper's surface shows telltale signs. Smooth plains that could be ancient cryolava flows and odd, bright patches that might be fresh frost from recent eruptions. Picture a geyser on Earth, but one that erupts with freezing liquids in the deep chill of space. If confirmed, this would make Kuiper one of the few Kuiper Belt objects with active geology, joining the ranks of Pluto and Europa. What's truly fascinating is how Kuiper's potential cryovolcanism ties into its ring mystery. If the world is geologically active, outgassing could be helping to replenish the ring, providing a steady supply of fresh particles. It's a delicate balancing act. Too much outgassing, and the ring would grow unstable; too little, and it would vanish over time. Yet somehow, Kuiper maintains this equilibrium, offering a masterclass in cosmic resilience. As we piece together Kuiper's puzzles, one thing becomes clear. the Kuiper Belt is a place of endless reinvention. Just when we think we understand the rules, objects like Quasar emerge, proving that the outer solar system still holds secrets we've only begun to uncover. Next up, we'll meet Quasar's enigmatic moon, Waywat, and explore how its quirky orbit might unlock even more surprises about this defiant world. Now, let's zoom in on Quasar's mysterious companion Waywat, a moon that dances to its own rhythm. Unlike most moons, which follow neat, circular orbits, Waywat traces a lopsided path around Quasar, almost as if it's being tugged by unseen forces. This irregularity isn't just a cosmic quirk, it's a clue to Quasar's hidden structure and the violent history of the Kuiper Belt. Scientists believe Waywat's wobbly orbit could be a fingerprint of Quasar's internal makeup. If Quasar isn't uniformly dense, say with a rocky core and an icy shell, its uneven gravity would nudge Waywat into that peculiar trajectory. Picture a lopsided spinning top. The way it wobbles reveals where the weight is distributed. Similarly, Waywat's path might be mapping out the secrets beneath Quasar's frozen surface. But there's another tantalizing possibility. Waywat's orbit could be the aftermath of a colossal collision. The Kuiper Belt is a cosmic demolition derby, with objects constantly smashing into one another. If Quasar was hit by another large body long ago, the impact could have sent debris flying, some of which coalesced into Waywat while leaving the moon's orbit permanently askew. This would make Waywat a living relic of that ancient crash, a silent witness to the chaos of the early solar system. What's even more intriguing is how Waywat's orbit interacts with Quasar's impossible ring. The moon's gravitational pull might be helping to sculpt the ring's shape, acting like an invisible hand that keeps the particles in line. Or if Waywat itself formed from ring material that clumped together, its irregular path could explain why the ring hasn't fully collapsed into a moon. It's a delicate gravitational ballet, with every step influencing the other. The puzzle doesn't end there. Waywat's dark surface, far less reflective than Quasar's, hints at a composition rich in complex organic compounds, stuff that could be the building blocks of life. How did such material end up on a tiny moon? Was it splashed there during a collision, or does it point to some deeper, unseen process at work in the Kuiper Belt? As we unravel Waywat's mysteries, we're not just learning about a single moon, we're piecing together the turbulent story of Quasar and the Kuiper Belt itself. Every irregularity, every gravitational nudge, is a sentence in a cosmic saga written in ice and rock. Next, we'll venture even further into the outer solar system to meet Sedna, a world so distant and solitary that its very existence challenges everything we know about orbital mechanics. Now let's journey to one of the most enigmatic wanderers in our solar system, Sedna. This distant world doesn't just push the boundaries of the Kuiper Belt, it defies them entirely. With an orbit so stretched it takes 11,400 years to complete a single trip around the Sun, Sedna is unlike anything else we've discovered. At its closest, it's still 3 times farther from the Sun than Neptune, and at its most distant, it ventures almost 1,000 times farther out. How did it end up on such a lonely, extreme path? The answer could rewrite our understanding of the solar system's history. One leading theory points to the gravitational hand of an unseen planet, something massive lurking in the frozen outskirts beyond Pluto. Imagine a hidden world, perhaps several times the size of Earth, whose gravity could have yanked Sedna into this bizarre orbit long ago. This idea isn't just speculation. It's part of the broader Planet 9 hypothesis, which suggests a distant giant might be shepherding several oddball objects like Sedna into similar stretched-out orbits. If such a planet exists, Sedna's path could be its calling card. But there's another cosmic suspect, a passing star. Billions of years ago, when our Sun was young, it likely formed in a dense cluster of sibling stars. One of these could have swung close enough to disturb Sedna's original orbit, flinging it into the deep freeze where it now resides. Computer simulations show this scenario is plausible. Sedna's orbit matches what we'd expect if a star gave it a gravitational kick long ago. The twist, if true, Sedna isn't just a relic of solar system history. It's a snapshot of the Sun's long-lost stellar family. Then there's the galactic tide, the subtle but relentless pull of the Milky Way itself. Over eons, the combined gravity of countless stars and dark matter in our galaxy could have gradually sculpted Sedna's orbit, like ocean tides reshaping a coastline. This explanation doesn't require a hidden planet or a rogue star, but it does demand patience. The process would have taken billions of years, making Sedna one of the oldest time capsules in the solar system. Sedna's secrets don't stop at its orbit. Its surface is one of the reddest in the Kuiper Belt, possibly coated in complex organic molecules cooked by eons of cosmic radiation. Unlike comets, which grow fuzzy comas when heated, Sedna stays eerily quiet, hinting that its frozen volatiles are locked away too deep to escape. This silence makes it a pristine relic, perhaps preserving chemistry from the solar system's infancy. As we ponder Sedna's origins, we're not just solving a single mystery, we're testing the limits of our cosmic neighborhood. Does a hidden planet lurk in the dark? Did a star once visit our solar system, or is the galaxy itself the architect of Sedna's solitude? Each clue pulls us deeper into the Kuiper Belt's grandest enigmas. Next, we'll examine Sedna's striking surface in even greater detail. What can its crimson hue tell us about the building blocks of the solar system? Now, let's turn our attention to Sedna's most striking feature, its blood-red surface. Unlike the muted grays and icy whites of many Kuiper Belt objects, Sedna stands out like a rusty beacon in the dark. What gives it this vivid hue? The answer might lie in the very building blocks of our solar system. Scientists believe Sedna's crimson color comes from a thick blanket of complex organic molecules known as tholins. These are not the kind of organics we find on Earth, no life here. Instead, they're the result of simple compounds like methane and nitrogen being bombarded by cosmic rays and solar radiation over billions of years. Think of it as cosmic cooking. Take basic ingredients, add a few eons of deep space weathering, and voila, you get a reddish sludge coating the surface. But here's the mystery. Most icy bodies, when warmed by the sun, release gases that form a fuzzy halo called a coma, like the ones we see around comets. Sedna, despite its dramatic color, shows no such activity. Why? The leading theory suggests its volatile ices materials that normally vaporize easily are buried too deep beneath its surface or locked away in a chemically altered state. It's as if Sedna's outer layer has been baked into a permanent crust, sealing its secrets inside. This makes Sedna a rare time capsule. While other Kuiper Belt objects have been reshaped by collisions or internal heating, Sedna's surface appears untouched, preserving chemistry from the solar system's earliest days. Its silence, no outgassing, no detectable atmosphere, hints that it spent nearly all its existence in the deep freeze, far from the sun's influence. The deeper we dig into Sedna's secrets, the more questions arise. Could its ultra-red material be common in the outer solar system, but usually hidden beneath fresher ice? Or is Sedna truly unique, a lone relic of some ancient chemical process we don't yet understand? Every observation peels back another layer of this distant world story. Up next, we'll shift our gaze to another Kuiper Belt oddball, a world that challenges our ideas about rings and rubble piles. But for now, Sedna's crimson face remains a tantalizing puzzle, one that might hold clues to the raw ingredients that built our cosmic neighborhood. Leaving Sedna's crimson mysteries behind, we find ourselves looking at a quieter but equally intriguing resident of the Kuiper Belt, 2002 MS4. This mid-sized world stands out not for flamboyant colors or dramatic orbits, but for what it lacks: moons. Unlike many of its neighbors adorned with satellites, 2002 MS4 appears to be a cosmic loner, drifting silently through the frozen expanse. What makes this object particularly fascinating is its rotation. While most Kuiper Belt objects spin relatively quickly, completing a full turn every few hours, 2002 MS4 takes its time roughly 11 hours to rotate once. This sluggish pace raises questions. Could its slow spin hint at a collision-free existence, untouched by the chaotic encounters that shaped other Kuiper Belt objects? Or does it suggest an unusually dense interior resisting the tug of external forces? Scientists suspect 2002 MS4 might belong to a purer class of icy bodies, pristine remnants of the early solar system. Without moons or significant disturbances, its composition could be closer to the original blend of ices and rock that existed billions of years ago. Think of it as a frozen time capsule, less altered by the gravitational shuffling that scrambled its neighbors. Its surface, likely a mix of water ice and dark organic compounds, might hold clues to the conditions present when the planets were still forming. But why so few moons? The leading theory points to location. 2002 MS4 orbits in a relatively quiet zone of the Kuiper Belt, far from the gravitational hotspots where frequent interactions might strip away moons or shatter them into rings. Its isolation could mean it never experienced the violent encounters that gave Pluto its entourage or Haumea its collisional family. Instead, it might represent a rarer breed, an undisturbed survivor from a time before Neptune's migration reshaped the outer solar system. This object's quiet nature challenges our assumptions. If 2002 MS4 truly is a relic of a calmer, earlier era, studying it could help us separate the original building blocks of the solar system from the chaos that came later. Its slow spin and moonless solitude make it a subtle but critical piece of the puzzle, one that reminds us not all mysteries announce themselves with flashy colors or extreme orbits. Sometimes the most revealing secrets are those whispered by the quietest worlds. Next, we'll encounter a dwarf planet with a surprising symmetry to Pluto, a world that mirrors its orbit like a cosmic shadow. But for now, 2002 MS4 unassuming presence offers a humbling lesson. In the vastness of space, even the lone wanderers have stories to tell. Now, shifting our gaze from the solitary 2002 MS4, we encounter a dwarf planet with a cosmic twist, Arrokoth, often dubbed the anti-Pluto. This nickname isn't just for show. Arrokoth shares an orbit nearly identical in size and shape to Pluto's, but here's the catch. While Pluto reaches its closest point to the Sun, Arrokoth is at its farthest and vice versa. It's as if these two worlds are performing a carefully choreographed dance, forever mirroring each other from opposite ends of their paths. This gravitational symmetry isn't just a curiosity, it's a window into how Neptune's influence sculpted the Kuiper Belt, locking objects like Arrokoth and Pluto into resonant orbits that have persisted for billions of years. What truly sets Arrokoth apart, though, is its moon, Vanth. Discovered in 2005, Vanth is unusually large for a Kuiper Belt satellite, about 1/3 the size of Arrokoth itself. Most moons in this region are tiny, but Vanth's substantial presence raises intriguing questions. Did it form from a colossal impact like Pluto's Charon? Or was it captured, snatched from the sea of smaller objects drifting through the Kuiper Belt? The answer could reveal how often such sizable pairings occur in the outer solar system, and whether they're relics of a more violent era. Then there's Arrokoth's surface, a patchwork of frozen methane and water ice. Unlike Pluto's dynamic heart-shaped glacier, Arrokoth appears more subdued, but don't let that fool you. Seasonal changes might still be at work here. When Arrokoth nears the Sun, traces of methane ice could sublimate, creating a transient, tenuous atmosphere before refreezing as it retreats. This cycle, if confirmed, would mirror Pluto's own seasonal shifts, suggesting that even in the Kuiper Belt's frigid depths, change is the only constant. Yet Arrokoth's most tantalizing feature might be its darkness. Despite its icy composition, the dwarf planet reflects very little light, hinting at a surface coated in complex organic molecules. These could be the products of methane breaking down under the relentless barrage of cosmic radiation, a process that might also explain its reddish tint. If so, Orcus could be a laboratory for understanding how radiation transforms simple ices into the building blocks of life. In the grand tapestry of the Kuiper Belt, Orcus stands as both a counterpart and a contrast to Pluto, a reminder that even in symmetry there's room for surprise. Its orbit mirrors a famous neighbor, but its secrets are entirely its own. And as we'll soon see, the Kuiper Belt has even more doppelgangers in store. Now, as we journey further into the Kuiper Belt's catalogue of curiosities, we arrive at Ixion, a world whose name carries the weight of ancient myth. In Greek legend, Ixion was a king condemned to spin eternally on a flaming wheel, and fittingly, this distant Plutino spins through the darkness with its own fiery secrets. Ixion's most striking feature is its color, a moderate reddish hue that sets it apart from its neighbors. This tint isn't just for show, it's a clue. The surface likely harbors complex organic compounds, the kind that form when methane and other simple ices endure eons of cosmic radiation. Imagine a cosmic painter slowly staining Ixion's surface over billions of years, leaving behind a patchwork of tholins, those same carbon-rich molecules that tint Pluto and Titan. But here's the puzzle: Ixion's redness isn't uniform. Some areas appear darker, others brighter, suggesting a surface sculpted by both chemistry and chance. Size is another enigma. Early observations pegged Ixion at around 650 kilometers wide, but recent studies hint it might be smaller, perhaps due to uncertainties in its reflectivity. A darker surface would mean a more compact size, while a brighter one could imply a puffier, less dense structure. This uncertainty isn't just academic, it shapes how we understand Ixion's history. If it's smaller and denser, it might be a primordial relic, largely unchanged since the solar system's birth. If larger and porous, it could be a rubble pile, reassembled after a catastrophic collision. Then there's the question of activity. Unlike Pluto or Eris, Ixion shows no signs of atmosphere or geological drama. Its surface seems frozen in time, a quiet counterpoint to the dynamic worlds we've explored earlier. Yet even here there's intrigue. The patchy distribution of organics hints at localized processes, perhaps ancient cryovolcanic vents or impact scars that exposed fresh ice to radiation. Some scientists speculate that Ixion's dark spots could be radiation shadows, where topography shielded patches of surface from space weathering, creating a spectral fingerprint of its past. What truly captivates, though, is Ixion's orbit. As a Plutino, it's locked in a 2-to-3 resonance with Neptune, completing 2 orbits around the Sun for every 3 of the ice giants. This gravitational dance places it in a club with Pluto and Orcus, yet Ixion's path is slightly more elliptical, stretching farther from the Sun at its most distant point. That extra stretch might explain why its surface appears less processed than Pluto's. It spends more time in the deep freeze, where chemical reactions slow to a crawl. In the end, Ixion is a paradox, a world named for perpetual motion, yet one that seems frozen in stillness. Its reddish tint whispers of slow, relentless change, while its uncertain size reminds us how much we still have to learn about these distant fragments of the solar system's youth. And as we'll soon see, the Kuiper Belt has even quieter, darker mysteries waiting in the shadows. Leaving behind the reddish enigma of Ixion, we now set our sights on Varuna, a cosmic whirligig spinning through the Kuiper Belt at breakneck speed. Picture a stretched-out potato tumbling end over end every 6 hours and 20 minutes, defying everything we know about how loose rubble piles should behave in the faint tug of deep space gravity. Varuna's most obvious oddity is its shape. Most small solar system bodies, especially those beyond Neptune, tend to settle into near-spherical forms under their own weak gravity. Not Varuna. Observations reveal it's distinctly elongated, stretching roughly twice as long as it is wide. That's akin to a snowball you'd squeeze between your hands before tossing, except in space without those hands. Normally, objects this large, about 680 kilometers across at their widest, should collapse into rounder shapes. Yet Varuna's rapid spin flings material outward at its equator, creating this bizarre stretched profile. This speed presents a puzzle. In theory, an icy rubble pile like Varuna, a loose collection of rocks and ices held together by gravity, should fly apart if spinning faster than one full rotation every 7 to 9 hours. The centrifugal force would overcome the weak gravitational glue, but Varuna laughs at these models, completing a day in just 6.3 hours without disintegrating. So how does it hold together? Some scientists propose its interior might be slightly denser than expected, providing extra gravitational pull. Others suggest a network of icy roots could thread through the rubble, acting like cosmic Velcro. Then there's the question of origins. Did Varuna form already spinning this fast, perhaps from a grazing collision that set it tumbling? Or could tidal forces from a past close encounter with Neptune have whipped it into this frenzy? The answers matter because Varuna isn't alone. Other mid-sized Kuiper Belt objects exhibit similar odd rotations. Understanding its cohesion could rewrite rules for how small, icy bodies evolve. Temperature adds another wrinkle. Varuna's surface hovers around -230 degrees Celsius, cold enough that methane and nitrogen ices behave like solid rock. Yet its rapid rotation means alternating sides bake briefly in sunlight every 3 hours, potentially creating stress fractures. Some researchers speculate this thermal cycling might help inflate the body, counteracting gravitational collapse and preserving its elongated form. Perhaps most intriguing is what Varuna implies about the early solar system. Its existence suggests that primordial collisions gentler than the smash-ups that created moons or families like Haumea's could have left behind these spinning oddities. They're time capsules of intermediate violence, neither fully shattered nor neatly reformed. As we continue our trek through the Kuiper Belt's menagerie, Varuna stands as a testament to nature's disregard for tidy models. It spins defiantly, challenging our assumptions while whispering secrets about the delicate balance between gravity, rotation, and the stubbornness of ice in the outer dark. And speaking of defiance, wait until you meet the next object on our list, a world where rings exist where they absolutely shouldn't. Now we turn our attention to a world cloaked in both mystery and irony, 2007 or 10, better known by its whimsical nickname, Snow White. This distant wanderer holds the peculiar distinction of being the largest unnamed object in our solar system, a title it's held for over a decade despite its significant size. Measuring roughly 1,230 kilometers across, it's larger than many of its named neighbors in the Kuiper Belt. Yet it lingers without an official title, a quiet giant waiting for its moment in the spotlight. Snow White's reddish hue sets it apart immediately. Most objects in this region display muted colors, dominated by charcoal grays and dull browns from ancient organic compounds. But Snow White's surface, likely coated in methane ice altered by cosmic radiation, gives it a distinctive ruddiness, like a rust-stained snowball drifting in the void. This coloration hints at complex chemistry playing out over billions of years, where sunlight and cosmic rays slowly transform simple ices into reddish organic sludge. Yet the real surprise came in 2016 when observations revealed Snow White wasn't alone. A small moon, barely 100 kilometers wide, danced around it. This discovery forced astronomers to recalculate Snow White's mass, as the moon's orbit betrayed secrets about the gravitational pull of its parent body. The presence of a moon also raised questions. Was this a fragment from a collision like many Kuiper Belt moons? Or did it form alongside Snow White, a frozen time capsule from the solar system's infancy? The water ice detected on Snow White's surface adds another layer of intrigue. While water isn't uncommon in the outer solar system, Its presence here suggests Snow White might have been active in the past, perhaps even venting material like a cryovolcano. Alternatively, the ice could be a relic of an ancient, pristine surface, untouched by the darkening effects of radiation. Either scenario makes Snow White a tantalizing target for understanding how these distant worlds evolve. What's equally fascinating is how Snow White escaped notice for so long. Despite its size, it reflects very little light, making it deceptively dim. Only deep surveys of the Kuiper Belt, like the one that discovered it in 2007, could have spotted such a faint object. Its delayed recognition speaks to the challenges of studying the outer solar system, where even substantial worlds can hide in plain sight. Snow White's story isn't just about one object, it's about the gaps in our knowledge. How many other large, dark bodies lurk unseen beyond Neptune? What processes paint some worlds red while leaving others gray? And why has this particular giant remained unnamed for so long? As we move forward, these questions remind us that the Kuiper Belt is full of surprises, each discovery rewriting what we thought we knew. Next, we encounter a binary system where two nearly equal-sized worlds orbit each other in a delicate dance, challenging our ideas about how such pairs form in the frozen reaches of space. Turning our gaze deeper into the Kuiper Belt's frozen expanse, we encounter a cosmic duo that defies expectations: Salacia and its companion Actea. This pair isn't your typical planet and moon system. Instead, they orbit each other like partners in a slow, graceful waltz, their sizes so similar that they blur the line between parent body and satellite. With Salacia measuring roughly 950 kilometers across and Actea just 300 kilometers smaller, their relationship challenges how we think about binary systems in the outer solar system. What makes this pairing truly fascinating is their dance. Circling each other at a distance of about 5,600 kilometers, they complete an orbit every 5.5 days. But here's the twist: their leisurely pace and wide separation suggest something unusual about their internal makeup. By calculating the gravitational forces at play, astronomers realized both bodies must have surprisingly low densities, only about 1.5 grams per cubic centimeter. That's lighter than a chunk of frozen water, implying these worlds aren't solid ice or rock. Instead, they're likely porous like fractured sponges, or perhaps hiding pockets of volatile ices beneath their surfaces. Theories about their formation are just as intriguing. Most binary systems in the Kuiper Belt are thought to arise from collisions where debris coalesces into moons. But Salacia and Actea's near equal size raises questions. Did they form together from a collapsing cloud of material like a miniature twin planet system? Or was their dance choreographed by a gentle gravitational capture, a rarity in the typically violent Kuiper Belt? Their nearly circular orbit favors the first idea, hinting at a shared origin in the solar system's early days. Then there's the mystery of their surfaces. Spectroscopic studies reveal water ice, but curiously, no clear signs of methane or nitrogen, common on larger Kuiper Belt objects. This absence suggests Salacia and Actea either lost these volatile compounds over time or never acquired them to begin with. Their dark, reddish hues, likely from radiation-processed organics, further imply ancient surfaces battered by eons of cosmic rays. Yet their low density raises another possibility. Could they still harbor subsurface reservoirs of lighter ices insulated from detection? The implications stretch beyond this single pair. If Salacia and Actea are porous, they might represent a class of fluffy, Kuiper Belt objects, worlds with weak internal structures that survived billions of years without collapsing. Alternatively, their low density could point to hidden layers of methane or nitrogen clathrates, ice-like compounds that trap gases in their crystal structures. Either scenario would rewrite our understanding of how mid-sized Kuiper Belt objects evolve. As we piece together Salacia's story, we're reminded how binary systems serve as cosmic scales, weighing the secrets of their components through motion alone. Their orbits whisper clues about internal structure, formation, and even the hidden chemistry of the outer solar system. And with every calculation, we inch closer to answering a broader question. Are these delicate duos the exception, or could they be the rule in the Kuiper Belt's quiet depths? Next, we'll explore another enigma, Haumea, a dark and water-rich object whose contradictions challenge our assumptions about surface evolution in the coldest reaches of space. Leaving behind the graceful dance of Salacia and Actea, we now turn our attention to a much lonelier but equally puzzling resident of the Kuiper Belt, Haumea. This dark, enigmatic world presents a cosmic riddle wrapped in layers of contradiction. At first glance, Haumea appears unremarkable, just another frozen body drifting in the distant dark. But peer closer and the mysteries begin to unfold. Measuring roughly 450 kilometers in diameter, Haumea stands out for two reasons. First, it's incredibly dark, reflecting only about 5% of the sunlight that reaches it, making it one of the least reflective objects in the Kuiper Belt. Second, despite this gloom, it boasts a surface rich in water ice, a combination that shouldn't exist under typical conditions. Normally, objects with abundant water ice are much brighter, like freshly fallen snow. So why is Haumea so dark while still holding onto its icy signature? The answer might lie in its complex rotation. Unlike most Kuiper Belt objects which spin in a steady, predictable rhythm, Haumea tumbles chaotically, its axis wobbling unpredictably over time. This erratic motion suggests a violent past, perhaps a colossal collision that left it spinning like a top knocked off balance. If true, that impact could have churned up darker material from beneath its icy crust, spreading it across the surface like a stain. Alternatively, the constant tumbling might expose fresh ice to space radiation over and over, slowly transforming it into a dark, carbon-rich sludge. Then there's the question of age. Is Haumea's surface a primordial relic, virtually untouched since the solar system's birth, or has it been relentlessly reshaped by billions of years of cosmic rays? Spectroscopy reveals methane trapped in its ice, a volatile compound that should have evaporated long ago unless protected somehow. Some scientists argue this methane is buried under a thin, insulating layer of darker material, preserved like a fossil. Others propose it's continuously renewed by cryovolcanic activity, a process where underground ices erupt to the surface, though no direct evidence of such eruptions exists yet. The presence of water ice complicates the picture further. On most dark Kuiper Belt objects, radiation breaks down surface ices over time, leaving behind tar-like organic residues. But Haumea's water ice remains detectable, implying either that its dark coating is thin enough for spectrometers to peer through or that fresh ice keeps emerging. One tantalizing theory suggests Haumea might be a transitional object caught in the slow process of losing its volatiles, with patches of ancient ice still clinging to life beneath a darkening veil. What makes Haumea particularly valuable to astronomers is its potential as a time capsule. If its surface is indeed primordial, it could offer an undisturbed snapshot of early Kuiper Belt chemistry. But if it's been altered, studying the exact nature of those changes could reveal how radiation and time transform icy worlds on cosmic scales. Future observations, especially by next-generation telescopes, might settle the debate by mapping its surface in unprecedented detail or catching the faint plumes of cryovolcanic activity. For now, Haumea remains a paradox, a dark world glistening with ice, a tumbler frozen in time yet potentially still evolving. Its contradictions remind us that even in the Kuiper Belt's quiet corners, nothing is ever as simple as it seems. And as we prepare to move forward, another oddity awaits. 2000 AW197, a curiously featureless object that challenges our understanding of surface diversity in the outer solar system. Now, shifting our gaze to another quiet giant of the Kuiper Belt, we encounter 2000 AW197, a world that defies expectations not by what it reveals but by what it hides. This massive object, roughly 700 kilometers in diameter, spins with an almost lethargic rhythm, completing a single rotation over 20 hours. But what truly baffles astronomers isn't its size or speed, it's the eerie blankness of its spectrum. Unlike the vibrant patches of methane, nitrogen, or organic compounds seen on Pluto or Makemake, 2000 AW197's surface reflects sunlight with almost no detectable features, like a smooth, unmarked canvas. Why would an object this large show so little surface variation? One possibility lies in its slow rotation. Unlike rapidly spinning bodies like Haumea, which fling material outward due to centrifugal force, 2000 AW197's leisurely spin might allow darker particles to settle uniformly, creating a dull, homogeneous blanket. Alternatively, its surface could be coated in a thick layer of photolytic sludge, a tar-like residue formed when methane and other ices are bombarded by solar radiation over billions of years. If this sludge is deep enough, it might mask any underlying geological diversity, like a veil draped over a sculpture. Then there's the question of heat. Larger Kuiper Belt objects often retain enough internal warmth from radioactive decay to drive geological activity. Think of Pluto's glaciers or Eris's possible cryovolcanoes. Yet 2000 AW197 shows no such signs. Is it simply too cold, its interior frozen solid, or could its featureless exterior hint at a dormant past with all its volatile compounds long since escaped or buried? Some researchers speculate that it might represent a dead end in Kuiper Belt evolution, a world that exhausted its geological potential early, leaving behind a static, unchanging shell. The contrast with other Kuiper Belt objects is striking. Take Varuna, another similarly sized body, which exhibits clear signs of water ice and rapid rotation. Or consider Ixion, whose reddish hue suggests complex organic chemistry. Why does 2000 AW197 lack these traits? One theory suggests it might have formed in a quieter region of the primordial disk, where fewer collisions or less volatile rich material led to a more monotonous composition. Another idea posits that its dark coating could be so uniformly thick that even powerful spectrometers struggle to glimpse the chemistry beneath. What makes this object particularly valuable is its potential as a baseline. By studying worlds like 2000 AW197, astronomers can better understand the range of possible surface conditions in the Kuiper Belt. Its blankness isn't just an absence of data. It's a clue about the limits of planetary processes in extreme cold and darkness. Future missions equipped with advanced infrared sensors might finally pierce its murky shroud, revealing whether it's a simple relic or a world hiding secrets beneath its somber exterior. For now, 2000 AW197 stands as a quiet enigma, a reminder that in the outer solar system, even the absence of features tells a story. And as we prepare to venture further, another distant traveler beckons 2014 UZ-224, a tiny world so far from the Sun that its very orbit challenges our understanding of celestial mechanics. Now, journey with me to the outermost fringes of our solar system, where shadows stretch long and time moves at a glacial pace. Here, we find 2014 UZ-224, affectionately nicknamed DD by astronomers. Discovered in 2014 by the Dark Energy Camera in Chile, this dim, slow-moving world quickly stood out for its staggering distance. Currently hovering around 92 astronomical units from the Sun, that's 92 times farther than Earth, DD takes an astonishing 1,100 years to complete a single orbit, crawling along at just 800 meters per second. To put that into perspective, if DD were a car on a cosmic highway, it would be rolling at a speed so slow you could outpace it on a bicycle. What makes DD remarkable isn't just its leisurely orbit, but the sheer challenge it poses to detection. Most telescopes struggle to spot objects this distant and faint. DD's discovery was only possible thanks to the Cerro Tololo Observatory's ability to scan vast swaths of sky over multiple years, catching the tiny shifts in its position against the stars. Even then, confirming its size, estimated at 630 kilometers in diameter, required the sharp eyes of the Atacama Large Millimeter Array, which detected the faint heat radiating from its icy surface. This technological triumph hints at how many more DDs might lurk undiscovered in the void, each a frozen time capsule from the solar system's infancy. But the real mystery lies in how DD and its kin ended up so far from the Sun. Traditional models of planetary formation struggle to explain why such sizable bodies exist in orbits so stretched and sluggish. One provocative theory involves dark matter, the invisible substance thought to permeate the galaxy. Some astrophysicists suggest that localized clumps of dark matter in the early solar system could have nudged objects like DD outward, like hidden hands gently pushing them into the abyss. While still speculative, this idea opens a tantalizing window into how unseen forces might shape the architecture of our cosmic neighborhood. DD's composition adds another layer of intrigue. Its surface, likely coated in water ice and dark organic compounds, reflects less than 13% of sunlight, making it one of the solar system's dimmer objects. Yet, despite its frigid temperature of just 30 Kelvin, some models suggest it could still harbor a thin atmosphere of nitrogen or carbon monoxide, clinging tenuously to its surface. If true, this would defy expectations for such a distant, cold world, proving that atmospheric processes can persist even in the deepest freeze. The story of DD isn't just about one oddball object, it's a test case for the limits of our knowledge. Every new discovery in this distant realm forces us to reconsider how planetary systems evolve and whether our current models are missing critical pieces. Upcoming telescopes like the Vera Rubin Observatory promise to reveal dozens more DDs, each with its own secrets. And as we piece together their histories, we might finally answer whether dark matter, rogue planets, or some other unseen force sculpted these solitary wanderers. For now, DD remains a humble yet profound reminder. Even in the farthest reaches of the Kuiper Belt, no world is truly insignificant. And as we peer deeper into the darkness, another wanderer demands our attention. 2005 RM43, a scattered disk object whose tilted orbit whispers of violent upheavals in the solar system's youth. Turning our gaze from the slow dance of DD, we encounter an object that seems almost rebellious in comparison. 2005 RM43, a scattered disk resident with an orbit tilted at a striking 28 degrees. Unlike most objects in the solar system that orbit close to the flat plane where planets formed, this icy wanderer carves a steep, looping path around the Sun, as if defying the cosmic norm. What makes 2005 RM43 so fascinating isn't just its tilt, but what that tilt reveals about the chaos of the early solar system. Most Kuiper Belt objects orbit within a few degrees of the ecliptic, the flat disk where planets like Neptune and Pluto reside. But scattered disk objects like this one break the mold with orbits that are both stretched and tilted, some as steep as 45 degrees. The question is, how did they get so dramatically knocked off course? The leading theory points to Neptune's turbulent youth. Billions of years ago, as the giant planets jostled for position, Neptune is thought to have migrated outward, its gravity flinging smaller bodies in all directions. Some were hurled into the inner solar system, while others, like 2005 RM43, were sent hurtling into high-inclination orbits. Imagine a game of cosmic pinball with Neptune as the bumper, each interaction sending objects careening onto wild new paths. But not all these journeys were random. Computer simulations suggest that Neptune's migration might have been more like a series of gentle nudges with resonant interactions, periodic gravitational tugs, steering objects into their peculiar orbits. 2005 RM43, for instance, might have been caught in a temporary dance with Neptune, a gravitational rhythm that gradually pushed it into its current steep trajectory. This could explain why some scattered disk objects share similar orbital angles, as if they were all herded by the same invisible hand. The object's physical properties add another layer of mystery. Observations hint at a surface rich in water ice and possibly complex organic molecules, common among Kuiper Belt objects but puzzling for something so far from the Sun. How did these volatile materials survive billions of years in the freezing void? Some scientists propose that 2005 RM43 might have originated closer to the Sun, where ices were more abundant before being ejected outward, a frozen refugee from a warmer past. Scattered disk objects like this one are more than just cosmic oddities, they're forensic evidence. By studying their orbits, we can reconstruct the solar system's violent adolescence, tracing the gravitational fingerprints of Neptune's migrations. Each tilted path is a clue hinting at how the giant planets reshaped their surroundings, and as telescopes grow more powerful, we may find even steeper orbits challenging our models anew. For now, 2005 RM43 stands as a testament to Neptune's far-reaching influence, a reminder that even the quietest corners of the Kuiper Belt bear the scars of ancient upheavals. And as we continue our journey, another object awaits, one whose defiance of orbital norms earned it the nickname Buffy. Now, let's turn our attention to one of the most rebellious members of the Kuiper Belt, a world so defiant of expectations that astronomers nicknamed it Buffy. Officially catalogued as 2004 XR190, this icy renegade orbits the Sun at a jaw-dropping 47-degree angle, a tilt so extreme it makes even the scattered disk objects we've discussed seem almost conventional by comparison. So what could fling an object into such a dizzying path? The answer may lie in two cosmic phenomena, gravitational resonances or a brush with a passing star. Let's start with the first theory. Over billions of years, the giant planets, especially Neptune, have acted like gravitational conductors, orchestrating the movements of smaller bodies through resonant interactions. Think of it like pushing a child on a swing. Timed nudges can send them higher and higher. Similarly, Buffy might have been caught in a rare, long-term resonance with Neptune, a rhythmic tug of war that gradually steepened its orbit over eons. Some simulations suggest that temporary resonances during Neptune's migration could have amplified Buffy's tilt without ejecting it entirely, leaving it stranded in this oddball trajectory. But there's a wilder possibility, a stellar intruder. Roughly 4 billion years ago, our young solar system was nestled in a dense star cluster with neighboring suns passing perilously close. A star venturing near the Kuiper Belt could have yanked objects like Buffy into extreme orbits with its gravity. Imagine a cosmic passer-by plucking a marble from a table suddenly. That marble isn't rolling in neat circles anymore. Intriguingly, Buffy's orbit isn't just tilted, it's also unusually circular for a scattered disk object, as if something smoothed out its path after tilting it. A stellar flyby could explain both quirks in one go. Then there's Buffy's composition, which adds another twist. Spectral observations hint at a surface coated in water ice and possibly methane, similar to quieter Kuiper Belt residents. But how did these volatile materials survive on an object that may have been hurled from the solar system's outskirts? One explanation is that Buffy formed closer to the Sun, where ices were abundant before being violently redirected. Alternatively, its icy shell might be a relic of cryovolcanism erupting internal oceans that refroze after its orbit was perturbed. Either way, Buffy's chemistry suggests a history far more complex than its label as a scattered object implies. What makes Buffy truly remarkable isn't just its odd orbit, but what it tells us about the solar system's resilience. Most models struggle to produce orbits as tilted as Buffy's without ejecting the object entirely. Its existence forces us to reconsider how chaotic the early solar system really was, and how delicate the balance is between stability and chaos. future discoveries of similarly extreme objects could reveal whether Buffy is a lone maverick or part of a hidden population of high-inclination survivors. As we prepare to venture deeper into the Kuiper Belt's mysteries, another enigmatic world awaits, one whose discovery reshaped our very definition of a planet. Now, let's journey even farther into the solar system's frozen frontier to meet an object so distant and mysterious it blurs the line between the Kuiper Belt and the Oort cloud. Officially designated 2012 VP-113, this icy wanderer has earned the nickname Biden after the vice president in office during its discovery, but its real claim to fame lies in its staggering orbit. With a perihelion, or closest approach to the Sun, sitting at 80 astronomical units, that's 80 times farther than Earth, Biden never ventures anywhere near Neptune's influence. Instead, it spends its entire existence in the desolate reaches of what astronomers call the inner Oort cloud, a hypothetical region of icy bodies bridging the gap between the Kuiper Belt and the sprawling spherical shell of comets that marks our solar system's edge. What makes Biden so captivating isn't just its distance, but how it moves. Like a cosmic rebel, its orbit aligns suspiciously with a handful of other extreme trans-neptunian objects, all clustered in a way that defies random chance. This peculiar grouping ignited one of the most heated debates in modern astronomy, the Planet 9 hypothesis. The idea is simple yet revolutionary. A hidden super-Earth, up to 10 times the mass of our planet, could be lurking in the outer solar system, its gravity shepherding these far-flung worlds into their strange, synchronized orbits. Biden's path, along with its celestial siblings, points like a compass needle toward where this unseen giant might hide. But let's break down the evidence. For such clustering to occur naturally without the pull of a massive perturber, the odds are astronomically low, less than 0.2%, according to some calculations. Imagine tossing a handful of confetti into the wind and watching every piece land in the same small circle. That's the level of coincidence we'd need to dismiss Biden's orbital alignment as random. Proponents of Planet 9 argue that its gravitational influence could explain not just the clustering, but also the orbit's shared tilt and their perihelia all landing on the same side of the solar system. Biden, in this scenario, is like a breadcrumb leading us to a much larger cosmic secret. Of course, not everyone's convinced. Skeptics propose alternative explanations, like the collective gravity of countless small Kuiper Belt objects or the lingering effects of a rogue star's ancient flyby. Yet these theories struggle to account for all the observed quirks as neatly as Planet 9 does. Biden's surface adds another layer of intrigue. Spectroscopic studies suggest it's one of the reddest objects known, likely coated in complex organic molecules called tholins, the same stuff that paints Pluto and Arrokoth in ruddy hues. This raises a fascinating question. How did such fragile compounds survive billions of years in the harsh radiation environment of the inner Oort cloud? One possibility is that Biden formed much closer to the Sun, only to be flung outward during the solar system's violent youth, carrying its primordial chemistry with it. The search for answers continues. Every new discovery of an extreme trans-neptunian object like Biden either strengthens the case for Planet 9 or forces us to rethink our models entirely. What's undeniable is that Biden and its kin represent something extraordinary, a population of worlds tracing the gravitational whispers of our solar system's untold stories. As telescopes grow more powerful, we may soon uncover whether these orbits are indeed the handiwork of a hidden giant or clues to an even grander cosmic puzzle. And speaking of puzzles, our next destination is another Kuiper Belt enigma, one that defies the very laws governing rings around celestial bodies. Now we turn our attention to a cosmic loner that might not even belong to our solar system. Meet 2008 ST-291, a faint speck of light drifting in the outer darkness with an orbit so peculiar it suggests a dramatic backstory. What makes this object extraordinary isn't just its distance, though at its farthest, it ventures over 1,000 astronomical units from the Sun, but the strange path it follows, one that hints at an encounter with forces we can't yet see. Unlike most Kuiper Belt objects, which trace relatively flat orbits aligned with the solar system's plane, 2008 SD291 moves at a steep tilt, cutting through this plane at a sharp angle. But here's the real puzzle. Its orbit also appears stretched, as if something massive once gave it a gravitational kick. Astronomers have run the numbers, and the math suggests this object's path can't be explained by the known planets alone. So, what's the culprit? One tantalizing possibility is that 2008 SD291 didn't originate in our solar system at all. It might be an interstellar immigrant captured from another star's Kuiper Belt long ago. Imagine this scenario, billions of years ago when the Sun was still nestled in its birth cluster alongside other young stars. A close encounter with a neighboring system could have plucked this object from its original home and sent it drifting into our own. If true, 2008 SD291 would join a rare club of suspected interstellar interlopers like the famous Oumuamua. But unlike Oumuamua, which blew through our solar system on a one-time visit, this object appears to be here to stay, forever bound to the Sun by gravity. The evidence for this capture theory lies in the details. 2008 SD291's orbit is more elongated and tilted than we'd expect for a native object, especially one so distant from Neptune's influence. Computer simulations show that while our solar system's chaos could stretch an orbit over time, it's far more likely that this object's path was shaped elsewhere before being handed off to the Sun's gravitational grip. Adding to the mystery, its surface, though too dim for detailed study, hints at a composition that doesn't quite match typical Kuiper Belt objects. Of course, alternative explanations exist. Some scientists argue that undiscovered, smaller bodies in the outer solar system could collectively nudge objects like 2008 SD291 into odd orbits. Others propose that the Milky Way's tidal forces, the subtle gravitational pull of our galaxy as a whole, might sculpt these paths over eons, but neither theory fully accounts for the object's extreme orbit as neatly as the interstellar capture idea. What's at stake here goes beyond a single icy wanderer. If 2008 SD291 truly is an immigrant, it opens a window into the dynamics of young star clusters and the swapping of material between nascent planetary systems. It also raises profound questions. How many other captured objects lurk in our solar system's outskirts? Could some of them preserve ices or organics from another star's cosmic neighborhood, offering clues about how planetary ingredients vary across the galaxy? As our telescopes peer deeper into the Kuiper Belt's shadows, each discovery like this one forces us to reconsider the boundaries of our cosmic backyard. Whether a lone interstellar traveler or a product of unseen local forces, 2008 SD291 reminds us that the outer solar system still holds surprises that defy easy classification. Next, we encounter a body whose very existence seems to bend the rules, a world with rings where none should survive. Now, let's journey even deeper into the solar system's shadowy fringes to meet a celestial oddball that sent shockwaves through the astronomy community. 2015 TG387, better known as the Goblin, discovered lurking 80 astronomical units. Sun, this enigmatic object doesn't just drift in the darkness, it practically taunts our understanding of the solar system's outer limits. What makes the Goblin so remarkable isn't just its distance, but the bizarre path it carves through space, an orbit so stretched and skewed that some scientists believe it might be pointing to the existence of a hidden, massive planet tugging at its trajectory. Picture this, the Goblin's journey around the Sun isn't a neat ellipse but a cosmic slingshot, taking a staggering 40,000 years to complete a single lap. At its closest approach, it still stays twice as far as Neptune, but at its most distant, it ventures an astonishing 2,300 astronomical units into the void, so far that the Sun would appear as little more than a bright star in its sky. Such an extreme orbit defies conventional explanations, and here's why. Normally, objects in the Kuiper Belt or scattered disk follow paths shaped by Neptune's gravity, but the Goblin's orbit is too elongated and tilted to fit that mold. Instead, its trajectory seems to cluster with a handful of other extreme trans-neptunian objects, all mysteriously aligned in a way that suggests an unseen hand is guiding them. This is where the Planet 9 hypothesis comes roaring in. Astronomers noticed that the Goblin and its distant cousins share orbits that appear to be shepherded by something massive, a hypothetical planet up to 10 times Earth's mass, lurking hundreds of astronomical units away. The math is compelling. Without such a hidden world, the odds of these objects having such similar, peculiar orbits by pure chance are astronomically low. The Goblin, in particular, became a linchpin in this theory because its discovery extended the pattern of these clustered orbits even further, tightening the noose around the idea that something big is out there waiting to be found. But the Goblin isn't just a clue in a planetary treasure hunt. It's also a fascinating world in its own right. Observations suggest it's likely a mix of ice and rock, with a reddish hue that hints at ancient organic compounds cooked by eons of cosmic radiation. Measuring roughly 300 kilometers across, it's too small to be shaped by its own gravity into a sphere, making it a rare glimpse into the primordial building blocks that never grew into full-fledged planets. Yet despite its modest size, the Goblin's influence has been enormous, reigniting debates about what might lurk in the solar system's uncharted territories. Of course, not everyone is convinced Planet 9 is the answer. Some researchers argue that the apparent orbital clustering could be an illusion caused by observational biases. After all, we've only spotted a handful of these extreme objects, and they're fiendishly hard to detect. Others propose that the collective gravity of smaller, unseen Kuiper Belt objects could slowly sculpt these orbits over billions of years. But even these alternative theories struggle to explain the precision of the Goblin's alignment with its distant peers. What's at stake here goes beyond just adding another planet to our textbooks. If Planet 9 exists, its discovery would rewrite the story of our solar system's formation, suggesting that our cosmic neighborhood once hosted additional massive worlds that were later ejected or drifted away. It could also explain other solar system mysteries, like the odd tilt of the Sun's axis or the peculiar orbits of some comets. For now, the Goblin remains a tantalizing piece of the puzzle, a ghostly signpost pointing toward answers we're still grasping to uncover. As our telescopes grow more powerful and surveys sweep deeper into the sky, each new discovery like this one peels back another layer of the solar system's hidden architecture. Whether the Goblin's orbit ultimately leads us to Planet 9 or forces us to rethink the outer solar system's dynamics entirely, one thing is certain: our cosmic backyard is far stranger and more wondrous than we ever imagined. Next, we encounter a pair of icy worlds locked in a silent dance, revealing secrets about the Kuiper Belt's binary systems. Shifting our gaze to another cosmic puzzle, we arrive at 2013 FY27, a dazzling duo in the Kuiper Belt that's turning heads for all the wrong reasons. This binary system isn't just another pair of icy worlds, it's a study in contradictions, with one member gleaming brightly while its partner wears a noticeably darker hue. What's causing this striking color divide? The answer might rewrite what we know about how these distant twins form and evolve. First, let's set the scene. 2013 FY27 is one of the brightest known objects in the Kuiper Belt, a fact that initially masked its true nature. When astronomers took a closer look, they realized it wasn't a single body but two worlds locked in a tight gravitational embrace, separated by roughly 20,000 kilometers, about half the distance between Earth and the Moon's orbit. The primary object measures around 740 kilometers across, while its companion clocks in at roughly 190 kilometers, making them a textbook example of a binary system where one member dominates the pair. But textbooks can't explain why the larger object reflects significantly more light, appearing almost snowy white compared to its darker, reddish partner. This color dichotomy isn't just a curiosity, it's a potential window into the system's history. One leading theory suggests the two bodies might have different surface compositions, baked under the same cosmic conditions for billions of years. The brighter world could be coated in fresh ices, perhaps methane or nitrogen that's periodically replenished by geologic activity, while its darker sibling might have lost these volatile compounds to space, leaving behind a crust rich in ancient, radiation-darkened organics. Alternatively, their contrasting colors could hint at wildly different origins. Imagine a scenario where the larger object formed closer to the Sun, gathering lighter materials before being flung outward, while its partner was always a darker, primordial relic of the outer solar system. Then there's the age factor. Surfaces in the Kuiper Belt are constantly bombarded by cosmic rays and micrometeorites, a process that gradually reddens and darkens ices over time. If one object has been more geologically active, say, with cryovolcanoes or landslides refreshing its surface, it could appear brighter simply because its skin is younger. The darker companion might represent an untouched time capsule, its hues preserving chemicals from the solar system's infancy. But here's the twist: binaries like this aren't supposed to have such dramatic differences. Most Kuiper Belt pairs are thought to form from the same swirling cloud of debris, which should leave them with similar compositions. 2013 FY27's mismatch challenges that assumption, forcing astronomers to consider whether some binaries might arise from later captures, where two unrelated objects become gravitationally bound after chance encounters. If true, it would mean the Kuiper Belt's population is far more dynamic than we've assumed, with objects routinely swapping partners over billions of years. The implications stretch beyond this single system. If binaries can form through multiple pathways, it complicates our efforts to use their properties, like color or composition, to trace the solar system's history. Worse yet, it suggests that some objects we've assumed are pristine might actually be cosmic hybrids, their surfaces altered by processes we're only beginning to grasp. 2013 FY27 is a reminder that even in the frozen reaches of the Kuiper Belt, appearances can be deceiving, and the stories these worlds tell are often more complex than they seem. As we piece together the clues from this enigmatic pair, our next stop takes us to an object that wears its age like a badge of honor: 2003 AZ84, a frozen time capsule with secrets of its own. Now we turn our attention to another fascinating resident of the Kuiper Belt, 2003 AZ84, a world that gleams like a cosmic mirror in the distant dark. This isn't just another icy body, it's a standout member of the Pluto family, named for its orbital dance with Neptune, much like Pluto itself. But what really sets 2003 AZ84 apart is its dazzling brightness, reflecting back more sunlight than almost any other object in its neighborhood. Why does this frozen world shine so intensely, and what secrets might its glittering surface hold? First, let's talk numbers. 2003 AZ84 measures roughly 680 kilometers across, making it one of the larger known Plutinos. But size alone doesn't explain its eye-catching reflectivity. While most Kuiper Belt objects have surfaces as dark as asphalt, this one bounces back about 20% of the sunlight that hits it, rivaling even Pluto's brightest regions. That kind of shine suggests something unusual is coating its surface, something far more reflective than the typical tar-like gunk found on most distant worlds. The prime suspect, methane frost, the same substance that gives Pluto its bright, icy patches. Here's where things get interesting. Methane shouldn't last long on surfaces this far from the sun. Solar radiation and cosmic rays should break it down over time, turning it into dark, reddish organic compounds. So how does 2003 AZ84 keep its frosty sheen? One possibility is that fresh methane keeps bubbling up from below, either through slow leaks or dramatic cryovolcanic eruptions. Imagine geysers spraying methane snow across the landscape, constantly repainting the surface with bright new layers. Pluto shows us this can happen. Its famous heart-shaped region, Sputnik Planitia, is a vast glacier of nitrogen and methane ice that's constantly renewing itself. 2003 AZ84 might be undergoing similar processes on a smaller scale, but there's a twist. Unlike Pluto, which has enough gravity to hold onto a thin atmosphere, 2003 AZ84 is too small for that luxury. Any gases that escape its surface would just drift away into space. This means whatever methane we're seeing must either be very recent or somehow trapped in a stable form. Some scientists think seasonal changes could be the key. As 2003 AZ84 slowly orbits the Sun over its 290 Earth-year trip, temperatures on its surface might shift just enough to allow methane frost to sublimate in some areas and refreeze in others, creating bright and dark patches that come and go like cosmic seasons. The similarities to Pluto don't stop there. Both worlds show evidence of complex geology despite their frozen exteriors. Pluto stunned us with towering mountains of water ice and glaciers flowing like soft putty, all powered by heat leaking up from radioactive elements deep inside. 2003 AZ84, while smaller, might harbor its own surprises. Could it have icy tectonics or even hidden underground oceans? Its high reflectivity hints at active resurfacing, which often points to internal warmth. The big difference is that without a spacecraft visiting 2003 AZ84, we're left piecing together clues from afar, relying on subtle changes in its brightness and color as it rotates. That rotation holds yet another puzzle. 2003 AZ84 takes about 7 hours to complete a full spin, fairly typical for a Kuiper Belt object. But light curves show its brightness varies more than expected, suggesting a surface that's not just frosty but also patchy. Some areas might be covered in thick methane deposits, while others expose darker, ancient terrain. This unevenness could be the fingerprint of past collisions, seasonal shifts, or even the slow creep of ice migrating from pole to pole over millennia. What makes 2003 AZ84 particularly intriguing is its potential to teach us about the diversity of Plutinos. These worlds share similar orbits, but as we're learning, their surfaces tell wildly different stories. Some are dark and red, others bright and icy. Some might be geologically dead, while others, like this one, could still be quietly active. Each variation offers a new piece of the solar system's history, helping us understand how materials were distributed in the early Kuiper Belt and how processes like radiation, impacts, and internal heating have reshaped these worlds over billions of years. As we continue unraveling the mysteries of 2003 AZ84, our journey takes us to one of the Kuiper Belt's earliest discoveries, a relic that's been watching the outer solar system evolve since the beginning, 1996 TL66. Now, let's step back in time to meet a true pioneer of the Kuiper Belt, 1996 TL66, one of the first scattered disk objects ever discovered. This wandering world doesn't just hold historical significance. Its chaotic orbit has become a key piece of evidence in unraveling Neptune's gravitational influence on the outer solar system. Unlike the relatively stable orbits of Plutinos, 1996 TL66 follows a path that's anything but orderly, stretching far beyond Neptune's reach before swooping back in. This extreme trajectory tells a story of gravitational upheaval, offering clues about how the giant planet sculpted the Kuiper Belt billions of years ago. When astronomers first spotted 1996 TL66, It challenged everything we thought we knew about the solar system's boundaries. Here was an object orbiting the Sun at an average distance of nearly 8 billion kilometers, so far out that it spends most of its time in the frigid, sparsely populated scattered disk, a region where objects are barely tethered to the Sun's gravity. Its orbit is wildly elongated, taking it as close as 3.5 billion kilometers from the Sun at perihelion and as far as 13 billion kilometers at aphelion. That's like swinging from the doorstep of Neptune to the edge of interstellar space and back over a single orbit lasting 550 Earth years. What makes this path so revealing? The answer lies in Neptune's turbulent past. Planetary scientists now believe that Neptune didn't form in its current position but migrated outward, its gravity flinging smaller bodies like 1996 TL66 into these stretched-out orbits. Imagine a cosmic game of pinball. Neptune's movement acted like the bumpers, sending icy objects careening into the outer dark. Scattered disk objects like this one are the survivors of that ancient chaos, their orbits frozen in time as records of Neptune's journey. But 1996 TL66 isn't just a relic, it's also a puzzle. Its orbit is tilted about 24 degrees relative to the solar system's plane, far steeper than most Kuiper Belt objects. This suggests it encountered more than just Neptune's gravity, perhaps a brush with another giant planet, or even the cumulative tug of passing stars over eons. The fact that it hasn't been ejected entirely hints at a delicate balance between disruption and stability, a dance of forces that's helped astronomers refine models of how planetary migrations shaped our cosmic neighborhood. The physical properties of 1996 TL66 are just as intriguing. Observations suggest it's roughly 550 kilometers in diameter, with a surface darker than fresh asphalt. Yet despite this dim appearance, its color is distinctly red, likely from cosmic rays bombarding organic molecules on its surface for billions of years. Unlike shiny 2003 AZ-84, this object wears its age openly, its hues betraying the relentless space weather it's endured. But even here, there are surprises. Some measurements hint at patches of slightly brighter material, possibly exposed by recent impacts or hidden cryovolcanic activity. What's truly remarkable is how much our understanding of Neptune's migration has evolved thanks to objects like this. Early models suggested a smooth, gradual movement, but the orbits of scattered disk bodies tell a story of fits and starts, even sudden jumps. 1996 TL66, with its extreme path, supports the idea that Neptune's journey wasn't a solo trek but part of a gravitational reshuffling involving Jupiter, Saturn, and Uranus. Each time these giants interacted, they sent shockwaves through the Kuiper Belt, leaving behind trails like breadcrumbs for us to follow. As we close this chapter on one of the Kuiper Belt's earliest known wanderers, we turn next to a newcomer that's pushing the boundaries of discovery even further. 2021 DR15, an extreme trans-neptunian object whose orbit might trace the faint fingerprints of unseen forces. Now, as we edge toward the final frontier of our cosmic journey, we encounter a mystery still fresh from the telescope's lens. 2021 DR15. This shadowy wanderer, discovered just 3 years ago, is among the most distant known objects in our solar system, drifting so far from the Sun that its orbit feels almost untethered. What makes 2021 DR15 extraordinary isn't just its remoteness, but the peculiar path it traces, a path that might hold secrets about hidden planets or even the gentle pull of our galaxy itself. At its farthest, 2021 DR15 ventures over 12.5 billion kilometers from the Sun, taking more than 6,000 Earth years to complete a single orbit. That's a distance so vast, sunlight takes nearly 12 hours to reach it. Yet what truly baffles astronomers is how its orbit aligns with a handful of other extreme trans-neptunian objects. Like breadcrumbs scattered in a cosmic forest, these objects' paths seem to cluster in a way that defies random chance, hinting at the gravitational tug of something unseen. Could this be the long-theorized Planet 9, a hidden giant lurking in the darkness, or does the answer lie in the collective influence of passing stars or the Milky Way's tidal forces? The intrigue deepens when you examine 2021 DR15's orbital tilt. Unlike most solar system objects which orbit in a relatively flat plane, this world's path is inclined by about 32 degrees. Such steep angles are rare and often suggest dramatic past encounters, perhaps with a rogue planet early in the solar system's history, or with Neptune during its outward migration. Yet 2021 DR15's orbit is too distant and stable to fit neatly into Neptune's scattering models. Instead, its trajectory aligns eerily well with predictions for how an undiscovered, Earth-sized or larger planet might shepherd distant objects into clustered orbits. But let's consider another possibility: galactic tides. Just as the Moon's gravity stirs Earth's oceans, the Milky Way's gravitational field exerts a subtle pull on the solar system's outer reaches. Over billions of years, this could sculpt the orbits of objects like 2021 DR15, nudging them into their peculiar alignments without requiring a hidden planet. It's a cosmic tug-of-war between two theories, and each observation of this distant object tips the scales slightly. What's astonishing is how little we know about 2021 DR15's physical traits. Its dimness suggests a surface darker than coal, likely coated in primordial organic sludge altered by eons of cosmic radiation. Yet even here, surprises lurk. Some spectral data hint at patches of water ice, a tantalizing clue that this world might have preserved ancient chemistry untouched since the solar system's birth. Every new observation peels back another layer, revealing just how much we still have to learn about these frozen sentinels at the edge of everything. As we stand on the precipice of discovery, 2021 DR15 reminds us that the Kuiper Belt isn't just a collection of icy relics, it's a dynamic frontier where the past and present collide. Whether its orbit whispers of unseen planets or galactic forces, one thing is certain: the outer solar system still holds stories we've only begun to read. And with that, we turn to the grand finale of our journey, where we'll weave together the mysteries of all 25 objects into a tapestry of cosmic wonder. As we bring our journey through the Kuiper Belt to a close, it's impossible not to marvel at the sheer strangeness of these distant worlds. From Arrokoth's snowman-like silhouette to Pluto's beating heart of nitrogen glaciers, from Sedna's lonely, stretched-out orbit to 2021 DR15's cryptic path, hinting at unseen forces, each of these 25 objects has rewritten the story of our solar system. They're not just frozen fossils, they're active participants in a cosmic drama, challenging everything we thought we knew about how planets form and evolve. Consider the patterns we've uncovered. Haumea spins so fast it's shaped like a football, while Kuiper defies physics with rings that shouldn't exist. Eris, more massive than Pluto, lurks in an orbit tilted like a defiant rebel, and Makemake's dark moon MK2 appeared out of nowhere, upending theories about how such satellites form. These aren't random quirks, they're clues about the violent collisions that shaped our early solar system, about the turbulent migrations of giant planets, and perhaps even about hidden worlds still waiting to be found. What binds them all together is their refusal to fit neatly into our textbooks. The Kuiper Belt isn't some quiet backwater. It's a dynamic, ever-changing frontier where the rules seem to bend. Take Pluto's underground ocean, kept liquid by forces we barely understand, or the way Sedna's surface, untouched for billions of years, might hold the purest chemistry from the dawn of our solar system. Even the orbits themselves tell a story, with objects like 2021 DR15 and Buffy tracing paths so steep and stretched, they point to gravitational upheavals we're only beginning to map. The real excitement lies in what's next. Missions like NASA interstellar probe, slated to launch in the 2030s, could fly past more of these enigmatic worlds, while next-generation telescopes like the Vera Rubin Observatory will scan the skies for new ones. Every discovery peels back another layer. What if we find more objects with rings or another dwarf planet with geysers? What if Planet 9 isn't a planet at all, but something even stranger? So here's where you come in. Space exploration isn't just for scientists, it's a shared adventure. Hit that subscribe button and ring the notification bell, because the next big discovery could happen any day. Will we finally spot Planet 9? Will a new mission reveal oceans under another icy crust? The Kuiper Belt has kept its secrets for 4.5 billion years, but not for much longer. Stay curious, stay tuned, and remember, the universe's greatest stories are still being written.